Okay, we're going to graph y equals 1/2 x squared and see what kind of impact that 1/2 has on our graph. So I'm going to make a table. This time I'm going to make a table with even numbers. And the reason I'm going to make a table with even numbers is because when I take half of a number, it's so much easier to take half of an even number than it is to take half of an odd number. So if I put a -4 in, I'm just going to remind myself right here that y is the same thing as 1/2 x squared. If I put a -4 in, -4 squared is 16. Half of 16 is 8. So left 4, up 8. When I put a -2 in, -2 squared is 4. Half of 4 is 2. So when I put a -2 in, I get a 2 in, out. And when you put a 0 in, half of 0 is 0. And when we put a 2 in, 2 squared is 4. Half of 4 is 2. And when we put a 4 in, no surprise, 4 squared is 16. Half of 16 is 8. And we knew that because, I said no surprise, because we've got that symmetry about that axis of symmetry there. So on the left, we've got the exact mirror image that we do on the right. Now what happens to our 1-3-5 rule? Our 1-3-5 rule was cut in half. So our 1-3-5 is cut in half to become 1/2. Half of 3 is 1.5. You know, I'm going to stay consistent, 1.5. Half of 5 is 2.5. If I went up to 7, half of 7 is 3.5. So we're going to go right 1 up 1/2. Right 1 up 1.5. Right 1 up 2.5. Right 1 up 1, 2, 3.5. So you can see more points when we use the 1-3-5 rule than when we just make a table of values. So in the next videos, we're going to practice the 1-3-5 rule with an a value other than 1. So here we have y equals -1/2 x squared. The negative just means that we have a reflect over x. And when we reflect over x, our parabola opens down. So we still have our vertex at 0, 0. And then instead of 1, 3, 5, we're going to have 1/2. Half of 3, half of 3 is 1.5. Half of 5 is 2.5. And then we could even go as far as 7. Half of 7 is 3.5. And if we had room, half of 9 is 4.5. So let's see how much of this we can get. So we're going to go right from our vertex, right 1, down 1.5, because it's got that reflection. Sorry, right 1, down 1/2. Right 1, down 1.5. So 1/2, 1. Right 1, down 2.5. So 1, 2.5. Right 1, down 3.5. 1, 2, 3.5. I've got my axis of symmetry, and I can reflect these points over the axis of symmetry here. It's just really art-like, right? It's like being in art class. Just make sure that your parabola has a curve and it's not that sharp turn there. It's definitely a curve and not a V. And that is our graph. So hopefully using this 1-3-5 rule will be helpful. Let's see what happens when we have y equals 2x squared. Now, I should have said also that, you know, what happened to our parent graph? You know, our parent graph was right 1 down 1, right 1 down 3, right 1 down 5. You know, this is our parent graph here in blue. And it looks very different. You know, it looks 1, 2, 3, 4, that's that point, and then 3, 9. So when we have that 1/2 out front, it makes the graph wider. Well, this 1/2, just like the reflect over x from the negative, the 1/2 gave us a vertical shrink. And a vertical shrink results in a wider graph. Wider from the parent. So let's see what happens when we have that 2 out front. Here we have y equals 2x squared. I know there's a table over there, but I'm going to ignore the table, and I'm going to see if we can use this 1-3-5 rule again. 1, 3, 5, and maybe even 7. We'll see. Now, because of this 2, we're going to have to take each one of those numbers, 1, 3, 5, 7, and instead of cutting it in half, we're going to need to multiply it by 2. So our rule goes from 1, 3, 5 to 2, 6, 10. 1 times 2 is 2, 3 times 2 is 6, 5 times 2 is 10. So we start at 0, 0. There's no reflection because there's no negative, and we're going to go right 1 and then up 2. Right 1, up 1, 2, 3, 4, 5, 6. And then right 1, up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can see that that is way off the graph. So when I draw that vertical axis of symmetry and I reflect my points over, this is not wide at all. This is not a vertical shrink. This is a vertical stretch. We've stretched this parabola and made it not wide, but skinny. So this is called a vertical stretch, which results in a skinny type of graph. And the larger that A value is, the skinnier our graph is going to get. Now I just want to demonstrate this real quick with the parent function. This is what the parent function looks like. So you can see what I mean by skinny. It makes the parent function appear as if it's wide. But it's not wide. That blue curve is y equals x squared. And the red curve is y equals 2x squared. So you can see that it's skinnier than the parent function. Okay, I'm pretty sure that you can do this one, y equals negative 2x squared. Go ahead and give this one a whirl and then press play and check your answer. I just used my 1-3-5 rule in my head, and I made it, instead of 1, 3, 5, I made it 2, 6, 10. The 10 I couldn't even begin to graph, but I was able to go right 1 down 2, right 1 down 6, and get enough points. If I were to make a table, when you put a -2 in, you can see that you get -8. And when you put -1 in, you get -2, 0, 0, 1, -2, and 2, -8. And those are all the points that I actually have on the graph too. So you can always make a table of values if you like, Or if you want to use the 1-3-5 rule, now you've got two different tools that you can use, whichever one you're most comfortable with, to graph these. Now I'm going to conclude real quick with what happens when A is positive. So this means A is positive. So what happens when A is greater than 0? When A is greater than 0, we have a parabola that opens which way? Does it open up or does it open down? The parabola opens up. And when it opens up, it has a minimum value. So it opens up, has a minimum value. When A is less than 1, meaning A is negative, the parabola opens down. It's a reflect over the x-axis. And when it opens down, it has a maximum y value. So sometimes I draw that picture just to get that visual. When A is between -1 and +1, so here we have -1 to +1. So when A is in between -1 and +1, the graph is wider. And that is a vertical shrink. And when A is less than -1, so this is what my colors are for here, when A is less than -1, that section right there, any value in that green section or any value in the green section to the right, the graph is going to be skinny. And that's not a vertical shrink, that's a vertical stretch. And then recall, when I add a constant outside of the function, that's a shift up C units. And there's a little graph for you there. And when we subtract C outside of the function, it's a shift down C units. So you may have to go back and recall these rules from when we graphed absolute value functions. And we graphed absolute value functions back a few chapters ago. It was probably three units ago, 3 or 4 units ago, that we graphed absolute value functions. So when we graph those, that's when you'll have your list of all your rules. We'll go over them again, but here are just 2 of them because those are the main 2 ones that we're going to be working with in the homework for this section. The vertex for this graph is 0, 0, y equals x squared. But when we have y equals x squared plus 3, we go up 1, 2, 3. So our x value remains 0 because we did not move left or right. We only moved up 3. So that's how our vertex is impacted. So hopefully you've got enough here from these lessons that you can give the homework a try and get some practice in there graphing, exploring quadratic functions, and then we'll graph more with left and right shift.